Hey, are there any questions before we start today's session? Can you hear me? Okay. Yeah, Abhinav, you have anything to say?
Uh, right now, I don't have any questions to ask.
Sorry?
Right now, I don't have any questions to ask.
Okay. Okay, so let us just recapitulate what we did last time. So we had uh, we had been discussing Lorentz transformation. We saw vector representation, and then we also discussed spinor representation, how a spinor transforms under Lorentz transformation. And after that, uh, we wrote down the algebra SO 1, 3 algebra satisfied by the generators of Lorentz transformation. And then we wrote down Dirac equation and shown that it is Lorentz covariant. Okay, so there are no questions from the previous session, so I'll start. So the plan today is to discuss Dirac equation further. And there was one question last time by Dhanush. I think he hasn't joined today, but if I remember the question correctly, he was asking whether these S rho sigma has any analog with the rotation and boost in general. But answering to that question, I said I'm not very sure last time, but it is actually the same thing, just that S rho sigma, these are the generators under which a spinor transforms. But Sij is still Sij are the rotation generators, still the rotation generators, and S0I are the generators corresponding to boost. But these are the generators under which a spinor transforms and not a vector. That's the only difference. Any four vector transforms under this M that we defined earlier while discussing the vector representation. So any vector transforms under this M mu nu, these generators. But spinors transform under Lorentz transformation under spinors transform under Lorentz transformation using those S mu nu vectors. So this is one comment I wanted to make before we start. So let us start today's session. Session 7. Okay. Okay, so let's write down the Dirac equation. So this is the Dirac equation. Where psi of x is basically a 4-component spinor. We usually suppress this spinor index where this a takes values from 1 to 4. Okay. We write it as psi of x. So this is the 4-component spinor. Which we also call Dirac spinor. And gamma mu are the 4x4 matrices that satisfy the Clifford algebra. Okay, and we choose a particular basis which is called chiral or Weil basis, in which the gamma matrices are as follows. Gamma 0 is 0, so this is a 2 by 2 0, 2 by 2 identity, and gamma I are 0 sigma I minus sigma I 0. So we define something called sigma mu, which is like identity and then sigma matrices, where sigma vector is sigma 1, sigma 2, sigma 3, that we are already familiar with, the Pauli matrices, and define something called sigma bar mu. This is just a notation, minus sigma. Okay, so these will be useful for today's whatever we will be discussing. So I'm just writing this down for completeness. Okay, so these are the things we discussed last time, and let's write down one property of these gamma matrices, which will also be useful as we proceed. So gamma mu dagger, so we know the Pauli matrices are Hermitian, so gamma mu dagger turns out to be gamma 0, gamma mu, gamma 0, as you can check from the Clifford algebra itself. So when you substitute 0, you identically get 1. That is what you would expect from this equation. And so gamma 0 dagger is gamma 0, and gamma I dagger is minus gamma I. Okay, fine. Okay, so now what we want to do is, just like when we started the scalar field theory, we wrote down the Lagrangian and the corresponding action by integrating by Lagrangian I mean Lagrangian density. We obtained the Lagrangian density, and from there we wrote down the equation of motion, Klein-Gordon equation of motion, by varying the action, by minimizing the action when we vary the field. So the same thing we want to do here. We wrote down the Dirac equation so far, but we want to see what is the Lagrangian corresponding to the Dirac equation. Okay, so does that Dirac equation also follow from minimizing some action, is what we asked. So we want to write down the Lagrangian density. Corresponding to the Dirac equation. Okay, so what is the property of a Lagrangian density? I mean, the basic property is that it has to be a scalar. The Lagrangian density has to be a scalar, then only the equation of motion that you get from the Euler-Lagrange equation of motion, that will be invariant under Lorentz transformation. So our goal is to construct a scalar out of these spinors psi. So these spinors are the fields now, just like pi was the field for the Klein-Gordon theory. So we want to construct scalar, and what do we mean by scalar? Under Lorentz transformation, it should transform as just like phi square. Under Lorentz transformation would just become phi square. So that's why we called phi to be a scalar. But now we have to construct a scalar out of the spinors that we have, out of the Dirac spinors that we have. And a naive guess is that psi dagger psi would be a scalar, because psi is a 4 by 1 matrix and psi dagger will be 1 by 4 matrix. So when you do this calculation, you should get a scalar. But that naive case actually doesn't work. Can somebody tell me the reason, if you know, why this psi dagger psi doesn't actually transform as a scalar under Lorentz transformation? In case you have watched lectures, it must be taught there. So I'm asking if anyone knows.
Ma'am, Lorentz transformation is for real, right? Here psi is complex. Lorentz transformations are done on real vectors, right? Like on space-time, Lorentz transformation is done, and here psi is fundamentally complex.
But we have seen, right, how a spinor transforms under Lorentz transformation. That is what was discussed under that spinor representation
Okay,
section.
okay. I didn't attended those classes, like last two classes, so I'm not that much aware of.
Okay, okay. So yeah. Okay, so I'll explain the reason. Before that, let me just tell you what is how a spinor transforms, because that is also going to be useful. So a vector transforms as any 4 vector. Call it I think we called it u last time. So u rho becomes, under Lorentz transformation, it becomes lambda rho sigma u sigma, where this lambda matrix was, how do we get this? We get it by exponentiating the generators of the Lorentz transformation. Omega mu nu are the parameters, okay, and we call the generators m mu nu. The entire thing is a matrix whose row and column are indicated by this sigma and rho and sigma indices. Okay, don't confuse between these indices and these. So these indices tell you which particular Lorentz transformation you are performing. So if mu nu turns out to be 0, 1, that means you are performing boost along x direction or the first direction. If mu and nu turns out to be 1 and 2, it means you are performing rotation about 1, 2 plane. Okay, and these are the corresponding generators. Okay, so this is how a 4 vector transforms. Transforms as, okay, now how does a spinor transform under Lorentz transformation? A spinor transforms under Lorentz transformation as psi, this transforms as lambda subscript half. I'll tell you why I'm writing that half here, just to distinguish it from what we had before for a vector representation, psi beta. Okay, where psi half, and half has to do with the fact that quantization of Dirac equation will give us spin half particles. Okay, and psi, sorry, why am I calling psi half? This is lambda, okay, sorry. Exponential of minus I by 2 omega mu nu S mu nu. Okay, where S mu nu are constructed, sorry, this is a bit of repetition but it's worth it. S mu nu was defined as, in terms of the gamma matrices, this way. Okay. Okay, and this is so alpha beta. And note one more thing, we are using same parameter for the spinor transformation as well as for the vector transformation. That is because we want to make sure that we are performing the same Lorentz transformation on both the vector as well as the spinor. So to be very specific, these spinors are functions of, the spinors are labeled by space-time locations, so they become lambda inverse x. Where this lambda, don't confuse this lambda with this lambda half. Lambda half is this definition and lambda is this definition. So x is a vector, right? X is a 4 vector. And also don't confuse a spinor with a 4 vector. So spinor is a 4 component object. This has nothing to do with a 4 vector. Okay, it's very important. Okay, so having said all of this, now let's try to construct the action or the Lagrangian density for the Dirac equation. So few more jargons are required. So let us see those. So what is S? What is Sij? What is Sij? So mu nu runs from 0 up to 3. Okay, so Sij would be I over 4 gamma I gamma j when I is not equal to j. What do we get? What was gamma I? Gamma I in chiral basis was defined as 0 sigma I minus sigma I 0. Okay, so Sij turns out to be, you can do this calculation, should I do it? I mean, you just need to do that multiplication and then use the properties of sigma matrices, Pauli matrices. So what is gamma I gamma j? 0 sigma I minus sigma I 0 sigma j minus sigma j 0. Okay, so minus sigma I sigma j 0 minus sigma I sigma j. Okay, and what is sigma I sigma j? Okay, we will do that. So let's substitute this in order to find Sij. This will be minus the commutation between sigma I and sigma j. 0 minus sigma I sigma j commutator. And this commutator is epsilon ijk sigma k, I times, there is a 2 as well. So 2I epsilon ijk sigma k, if we substitute it, we get Sij half of Are there any questions?
Ma'am, here S of ij is a generator for Dirac spinner, right?
Exactly. Generator generating rotation for a Dirac spinner. Yes.
Rotation and boost. Boost?
Ij is only rotation. 0
Okay.
I will be boost.
Oh, yeah,
Boost.
yeah, okay,
Yeah.
okay.
Yeah. So we have written down what is Sij. So this I wrote down. This we made this observation last time, but since we are going to deal with this now, so I'm just repeating it again. So what do you see that Sij, if you take dagger of it, this is Sij still, right, because Pauli matrices are Hermitian. So you see that the generators corresponding to rotation for the Dirac spinner are Hermitian. Now let's look at the generators which generate boost. Okay, so S0I will be I over 4 gamma 0 gamma I. Okay, uh, so this is gamma 0 gamma I minus gamma I gamma 0. We can do that multiplication and write down explicitly what this matrix is. So gamma 0 is 0 identity 0, and gamma I was sigma I minus sigma I 0. Okay, so we get minus sigma I here, and 0 sigma I. Okay, yeah. So gamma I gamma 0 will be sigma I 0 0 and minus sigma I. So when you subtract the two, what do you get? Minus, so 2 times, so that 2 gets cancelled out with that 4. We are left with minus sigma I 0 0 sigma I. You agree? So now what do you see? The observation is that these generators are actually anti-Hermitian, right? So these are anti-Hermitian. Okay. Let me know if you have any questions at this point. Okay, so our naive case was that in order to get the Lagrangian out of the Dirac spinners, which has to be a scalar, of course. Our naive case was make psi dagger psi, which is what I was telling. Yeah, now why? But this doesn't work. because if you do this transformation under Lorentz transformation, how should a scalar transform? It should become psi dagger psi, but it doesn't become psi dagger psi
Because it's anti-Hermitian?
exactly.
Okay.
Exactly. Because, so let's see explicitly what we mean. So psi dagger psi will become psi dagger lambda half dagger lambda half psi. Okay, because psi under Lorentz transformation transforms as lambda half psi. So psi dagger will transform as psi dagger lambda half dagger. Since, so let's make it explicit for everyone to understand. So lambda half was exponential of minus I by 2 omega mu nu s mu nu. Okay, so if we only think of rotation, for rotations alone, what would it be? Lambda half will be exponential of, suppose boosts are generators, sorry, the parameters corresponding to boosts are all 0, so we only have rotations in lambda half. So let's just write it as, sorry, I am talking about rotation, ij. Now you have seen that Sij is Hermitian. What does that imply? If you take dagger of this, what do you get? Exponential of that I will become minus I, so you get I by 2 omega ij, then Sij dagger. We have seen that Sij dagger is nothing but Sij. So I over 2 omega ij Sij, since these are Hermitian. So this is what? This is nothing but lambda half inverse. So what do you see for rotations? Lambda half dagger, lambda half is 1. Okay, but if you have boost, but for boost what was, so the same argument follows. Now what will you get? So you will no longer get lambda half inverse when you take dagger of it, but you will get back that same thing. So I'm calling, so for boost mu nu take values 0 and I. If you take dagger of it, you get, so I becomes minus, but S0 I dagger is also minus S0 I. So you get back lambda half minus S0 I. Okay, so which implies now lambda half dagger, lambda half is no longer 1. Now okay, so and this further implies that psi dagger psi is not a scalar. Okay, because it doesn't transform like a scalar should, because this is not equal to 1. Okay, now this particular observation that Sij dagger is Hermitian, S0 I is anti-Hermitian, this particular observation we have made by considering a particular basis which we call Weil basis for the gamma matrices. But that is in general true, that you cannot have any finite dimensional representation for this Lorentz generators, any finite dimensional representation which will give you unitary, this lambda half matrix. So let me make that precise what I mean. So in general there doesn't exist any unitary transformation, sorry, any representation. Let me write it down. There doesn't exist any finite dimensional representation of this gamma mu matrices which can lead to unitary representation of Lorentz transformation. Of the spinor, of the Dirac spinors. So let's see why we are saying that. So let's remember what was our Clifford algebra satisfied by the gamma matrices. So gamma mu, gamma nu was 2 g mu nu, okay, where g mu nu is in the diagonal 1, minus 1, minus 1, minus 1. Now lambda half is exponential of minus I over 2 omega mu nu s mu nu. So lambda half dagger is equal to exponential of I by 2 omega mu nu s mu nu dagger. Okay. So for this to be unitary, for lambda half to be unitary, S mu nu must be Hermitian always for all mu nu. But now what was S mu nu? This was I over 4 gamma mu gamma nu. Now we are not substituting any, we are not assuming any representation for these gamma matrices the way we did before. So we consider this while basis, right? That is what we are not doing right now, but we are trying to argue this generally, most generally, that this is the case, that this lambda half matrices can't be unitary. So if we take dagger of this S mu nu, what do we get? Minus I over 4 gamma nu dagger, gamma mu dagger. This nu and mu indices are getting exchanged because when you take dagger, matrices exchange, right? Gamma nu dagger is equal to gamma nu gamma mu. Gamma nu dagger, gamma mu dagger. So that's why mu and nu got flipped, and also there is minus sign because of this I. Okay. Now what is gamma mu dagger? This is what we wrote initially. So I'm not going up because it gets difficult sometimes. So I'll write it down again. So gamma mu dagger was gamma 0, gamma mu, gamma 0. Okay. So if we substitute that here, what do we get? Plus gamma 0, gamma mu, gamma 0. Okay. So this is,
Ma'am,
yeah,
you removed minus sign.
where? Okay, here.
Ah.
Because I have flipped these two here.
Oh, okay, you flipped. Oh, yeah, fine. That's
Yeah.
fine. Sorry.
So we obtained S mu nu dagger is equal to gamma 0 S mu nu gamma 0. Okay. So sorry, did I make anything? Just a moment. I think it's fine. This was the definition, right? Or oh, okay. Yeah, we used I think. Um, sorry. Yes. Okay, fine. So yeah, so this is what S mu nu dagger turns out to be. This is fine. Now the point is that, so S mu nu dagger is, so what did we say? That for lambda half to be unitary, S mu nu must be Hermitian for all mu nu, right? Then only it will become lambda half inverse. Now what do we see here? So for S mu nu dagger to be S mu nu, we don't even have to go to this step, but this will be useful later on. So this is gamma nu dagger, So what do we see? We must have gamma mu dagger equal to gamma mu for lambda half to be unitary, right? Then only you will get S mu nu. But we have already shown that this is actually gamma 0 S mu nu gamma 0. So this is actually not possible, or this can also be explained in a different way, that gamma mu dagger equal to gamma mu for all mu But from Clifford algebra, you know that gamma 0 square is identity, but gamma I square is minus 1. So from here also you can see that you can never go to a basis in which all these gamma matrices are Hermitian. You see the point? Because what does it mean? You can, in a particular basis, this gamma 0, gamma I, all of these can be diagonal. So you have entries in the diagonal, let's say A, B, C, D. And when you square it, you are getting identity for gamma 0. But for gamma I, when you square it, you are getting minus 1. What does that imply? It implies the eigenvalues corresponding to the gamma I matrices are actually not real, but these are imaginary. And whenever you have imaginary eigenvalue, so gamma I dagger cannot be gamma I, right? It will pick up a minus sign. So from here also you can see, without choosing any particular basis, you can see that you can never have any representation, any unitary representation for Lorentz transformation of the spinors, no matter what basis you choose for your gamma mu matrices. So this is an important thing, but it's aside. So just so is this clear? Are there any questions? What I said, everything clear? Ask me now. Otherwise, we'll proceed with what we wanted to do.
So basically you are saying is like no matter what kind of basis we are taking for the gamma matrices, like we can't make this generator of a spinor as a
Hermitian.
unitary.
Yeah, you
Okay.
cannot make generator Hermitian, which implies
Okay.
that your the representation or the representation using which your spinor transforms and a Lorentz transformation, that can't be made unitary.
Okay. Okay.
Yes, that's the point. Yes. Okay. And for S mu nu to be Hermitian, it turns out that this gamma matrices should be Hermitian, because S mu nu dagger is I over 4 gamma mu dagger gamma nu dagger. So for this to be Hermitian, sorry, people will get confused if they do not watch the video but just see the lecture, the notes. So I shouldn't write there S mu nu. So okay, let me write one sentence. For S mu nu to be Hermitian, it turns out that gamma mu dagger should be equal to gamma nu. Okay, and then we are saying, but see from the Clifford algebra, we know that gamma 0 square equal to 1, gamma I square equal to minus 1. So this implies we can choose gamma 0 to be Hermitian, because you know the eigenvalues corresponding to Hermitian operators are real. So when you are squaring it, you are basically squaring the eigenvalues. And if that turns out to be 1, that means you can choose gamma 0 to be Hermitian, but not gamma I at the same time. If instead you choose your G mu nu to have that sign where the first one is minus and the remaining 3 are plus, then that would imply you can choose your gamma I to be Hermitian but not gamma 0. So at the same time all gamma mu cannot be made Hermitian, which means all S mu nu, there are 6 of it in 4 dimension, all S mu nu cannot be made Hermitian, which means gamma half is not unitary. Okay. This implies cannot be made unitary. Okay, so having said this, now we have so far seen that psi dagger psi is not a scalar. So what is the remedy? So let's make 2 more observations. S mu nu. So we have seen that Sij dagger is Sij. For rotation, the generators are Hermitian, and S0I dagger equal to minus S0I. Now let's see what happens to this commutator, Sij gamma 0 commutator. This is I over 4. So of course when I not equal to j, otherwise it will be 0. So I over 2 gamma I gamma j gamma 0. Okay. What is this commutator? Gamma I gamma j gamma 0 minus do they commute? Gamma 0 commutes with Sij, let's see. So it becomes gamma 0 gamma I, anti-commutator is equal to 0. So it means gamma 0 gamma I equal to minus gamma I gamma 0, right? You agree? So if we use that here,
Wait. Okay, this Poisson in bracket. Oh, fine. Okay.
Yeah, anti-commutator. This is anti-commutator. So if you change the position of gamma 0 twice, you will pick up 2 minus signs, which will make it plus. So this is the first term becomes same as that of the second term. So that means this is 0. Okay. And if you see this relation now, S0I gamma 0 anti-commutator, then that turns out to be gamma 0 gamma I this is equal to plus, okay. So what is it? We can flip these two, but that will pick up 1 minus sign, I over 2 minus gamma 0 gamma I plus gamma 0. So this is 0. Okay. So these are the 2 observations we have made. Now let's define psi psi dagger, which is as follows: psi bar, which is equal to psi dagger gamma 0. Now let's see what happens to the Lorentz transformation of psi bar. Psi bar will become psi dagger lambda half dagger, gamma 0 will remain as it is. Sorry, whatever it is, lambda half dagger. Okay, but okay, let's remember what was lambda half: minus I over 2 omega mu nu is mu nu. And let's look at rotation. For rotation, lambda half dagger we know equal to exponential of minus I over 2 plus I over 2 omega ij is ij, right? Because that is Hermitian. Now if we multiply by gamma 0 from right, this is I by exponential I by 2 gamma 0. Okay, don't forget that this itself is a 4 by 4 matrix. Okay, this is not just a number. Don't think of it as a number. So because Sij is matrix, okay, so what happens when we take gamma 0? If we want to pull this gamma 0 to the left, what will happen? It has to pass this Sij matrix, right? But we have seen that Sij and gamma 0 commutes. That means Sij gamma 0 is equal to gamma 0 Sij. So we can write this down as gamma 0 exponential I by 2 omega ij Sij. Okay, so this is gamma 0 lambda half inverse. Are there any confusion so far? Okay, great. Now that is for rotation. Now for boost, what will happen? We know that lambda half dagger for boost will become I by 2 omega 0 I. S0 I dagger is minus S0 I. Okay, so this is what we get for boost. Now multiply by gamma 0 from right. What have we seen? We have seen that gamma 0 I, sorry, S0 I, gamma 0 anti-commute, which means S0 I gamma 0 is equal to minus gamma 0 S0 I. So if we want to pull that gamma 0 to the left, we pick up a minus sign. That means it becomes exponential plus I over 2 omega 0 I S0 I. Okay, which is gamma 0 lambda half dagger. So this implies psi bar under Lorentz transformation, which became psi dagger lambda half dagger gamma 0, that is actually equal to psi dagger gamma 0 lambda half inverse for all nu and nu, for rotation as well as for boost. So this is nothing but psi bar lambda half inverse. Now if we make a bilinear like psi bar psi, how will it transform under Lorentz transformation? Psi bar transforms as psi bar lambda half inverse, psi transforms as lambda half psi. So this is 1. Therefore psi bar psi transforms as a a scalar. Is that good? Any questions so far?
Just a minute, just a minute.
There is one alternative way of understanding this. Let me say that as well, but first let me know if you have any questions on this.
Ma'am, this is for only rotations or for boost also?
Yeah, so that's the point. So for rotation, this lambda half dagger become lambda half inverse. Okay, and then but it is multiplied by gamma 0. We are multiplying it by gamma 0 because that's how we have defined. So this is by intentionally we are defining it this way so that we can ultimately get a scalar. Now the point is, here you have gamma 0 on the right side. We want to pull it to the left in order to get psi bar at the end. So it is psi dagger, lambda half dagger, gamma 0. Our intention is to pull it here so that with psi dagger and gamma 0 we can again write down psi bar. Now for rotation, lambda half dagger is lambda half inverse. This is lambda half inverse. This is lambda half inverse. But another observation that we made, that gamma 0 and Sij actually commute. So if we pull that gamma 0, this gamma 0 to the left of this lambda half inverse, we don't pick up any minus sign here. So that remains lambda half inverse. Okay, so lambda half dagger gamma 0 equal to lambda 0 gamma half inverse for rotation. Now what happens for boost? For boost, when you take dagger of that lambda half matrix, this becomes I becomes minus, but there is another minus sign coming from the anti-hermiticity property of this generator. So ultimately it remains lambda half. But now when you multiply by gamma 0 from right and you want to pull this to the left, from our observation that S0I and gamma 0 anti-commute, we know that S0I gamma 0 equal to minus gamma 0 S0I. So that's why when you pull that to the left, you pick up another, where have I written that? Oh sorry, that was for rotation, sorry. So when you pull that to the left, you pick up another minus sign. So this minus become plus, and that is nothing but lambda half inverse. So you see, for both rotation as well as for boost, lambda half dagger gamma 0 becomes gamma 0 lambda half inverse. That's why psi bar vector under Lorentz transformation becomes psi bar lambda half inverse. Is this clear?
Yeah, okay. Because for boost it was written something different before, right? So I was thinking this works only for rotation. Yeah, now it's fine.
No, but what was written differently? Let me know.
For boost, just go down.
Go down.
Down.
Okay.
Yeah. So for boost, here, gamma dagger of half gamma lambda dagger of half gamma 0 is before written as gamma 0 of lambda dagger half. So now once you change to minus sign, then it works. Yeah, now it's fine.
Oh yeah, that was mistake. By mistake I wrote that.
No, that's fine. That's fine. Now I got it. No, that's why I was doubting whether it is only working for rotations.
I understand your confusion. Yeah. Okay, great. So another way to see this without going through this much, but from how, okay, so we have seen that S mu nu dagger was equal to gamma 0 S mu nu gamma 0. This is what we proved in that here. So we here we have shown that. Now if you use that property, what happens to lambda half dagger? So lambda half dagger is exponential of minus I by 2 omega mu nu is mu nu dagger. So that dagger will basically get translated to, so minus I will become plus I and S mu nu dagger. This is equal to exponential I by 2 omega mu nu gamma 0 S mu nu gamma 0, which we can further write as gamma 0 exponential I by 2 so this is gamma 0 lambda half inverse gamma 0. So what do you see? You see that if you now multiply from right by gamma 0, so you got lambda half dagger equal to this. If you multiply by gamma 0, it will become inverse gamma 0 square, but gamma 0 square is identity from the Clifford algebra. So this is it. This is what we were showing explicitly, but this is another way of seeing the same thing that we said here. Okay. Okay. Good. Now, so we have obtained psi bar psi, which is a scalar, so which we can have in the Lagrangian in order to have Dirac equation. But what else? What was Dirac equation? It was I gamma mu del mu minus m psi equal to 0. So the natural guess would be there should be another quantity psi bar gamma mu del mu psi, right? But this should also be a scalar. Is that happening or not? Let's see. Is this a scalar? So under Lorentz transformation, how would it transform? It would transform as okay. Psi bar gamma mu del mu psi, okay. This is equal to so psi dagger, sorry. Now let's replace that lambda half dagger, what we obtained. This is gamma 0, lambda half inverse gamma 0. So this entire thing we can substitute to be lambda 0, gamma 0, lambda half inverse. Then we are left with gamma mu lambda inverse sorry, what happened, del nu, but we can also take this lambda half here because they commute psi, and this del nu doesn't act on lambda. So let me know if you get confused at any step. This is psi dagger. Now psi dagger gamma 0 becoming psi bar. Okay, and we have seen in our last session that lambda half inverse gamma mu lambda half is nothing but lambda mu sigma gamma sigma. This is what we proved last time, so I will not go over it. Here, so this is the relation we are using. Okay, this we proved infinitesimally. Let me just tell you. So this was lambda half and this was lambda. So this is lambda half inverse. We are expanding this infinitesimally, which means this omega parameter is small. We retain up to first order in omega, so that is what is lambda half inverse. This is lambda half. This was lambda matrix, this one again retained up to first order in omega, and then this left hand side boils down to then this entire equation boils down to showing this particular relation, and this is what we derived earlier in this session only, that relation here, and this relation turns out to be equal to that right hand side. This was the vector representation of the generators corresponding to a 4 vector, that if we multiply by gamma nu, that thing becomes identical to this left hand side. So this is how we proved that relation. We will not do it now, but if you have forgotten, you can get back and look at it. So let's use this relation now. So this is psi bar. Now this is equal to lambda mu sigma gamma sigma. Okay, then we have lambda inverse so this is equal to psi bar delta mu sigma gamma sigma del nu psi, which is nothing but psi bar gamma nu del nu psi. Nu is just a dummy index, we can change it to mu. Okay, so it indeed transforms as a scalar. So psi bar psi is indeed a scalar. Okay, therefore the Lagrangian density can be written as psi. Okay, so this is the Dirac Lagrangian. Okay, so the Euler-Lagrange equation should give you back the Dirac equation. You can treat psi and psi bar to be independent, just the way we were doing for complex scalar field when we had phi and phi star in our Lagrangian. So Euler-Lagrange equation for psi bar will give you exactly the Dirac equation. You see that, right? This is what was the Euler-Lagrange equation. It was del mu psi bar minus psi bar equal to 0. But you don't have derivative acting on psi bar, so this term is 0, and from that term you get only this part. So this implies I gamma mu del mu minus m acting on psi equal to 0. And Euler-Lagrange equation for psi would be what would it be? It is I psi bar gamma mu. Okay, from the second term we get m psi bar. Okay, this equation sometimes is also written as psi bar I gamma mu del mu, which is acting to its left, minus m. Okay, remember this gamma and psi both are vectors, so you shouldn't flip their order. But since when we say that this is acting to the left, it is basically acting on psi bar but not gamma. These are those matrices which satisfy Clifford algebra. They are independent of x. Okay, so this is the Lagrangian and the corresponding Euler-Lagrange equations. This is the Hermitian conjugate version of the Dirac equation. You see that, right? Why we are saying that? If you take this particular equation, I gamma mu del mu psi minus m psi, this is what you have. If you take Hermitian conjugate, take its Hermitian conjugate, take Hermitian conjugate, so you get minus I. You have to remember that psi is a 4 component object and gamma mu, these are all 4 cross 4 matrices. So it means that you should keep in mind the order. So it will become minus m psi dagger equal to 0. Okay, so that implies minus I, let's take minus common, so del mu psi dagger gamma mu dagger plus m psi dagger equal to 0. Now you use that property of gamma matrices. We have said at the beginning of our class that gamma mu dagger is gamma 0, gamma mu, gamma 0. So let's use that. Gamma 0 plus m, there will be a plus in between because there is this minus here. So when you take del L del psi, that will give you minus m psi bar. Okay, because of this minus sign, this is del L del psi. So that minus will make this minus plus, so you get a plus here. Okay, so yeah, so this gamma mu dagger is this, and then you have m psi dagger equal to 0. So again you can write that psi bar, our definition, gamma mu gamma 0 plus m psi bar psi dagger equal to 0. Now multiply by gamma 0 from right, then what will you get? Gamma 0, when it hits this gamma 0, it becomes 1, it becomes gamma 0 square, so that's 1 plus m psi dagger gamma 0 you get, that's nothing but psi bar. Okay, so that is what we had here. So this is nothing but Hermitian conjugate of the Dirac equation. But I just did these steps so that you are very clear about how to what to apply where, I mean which thing. Yeah. Okay, now okay, let me pause here and ask if there are any questions so far. Okay, if not, what we can do next is talk about Weil spinner. These are 2 component spinners. Sorry, this is still a 4 component spinner, but now this psi L, psi R, both of these are 2 component spinners, where psi L is called left-handed Weil spinner, let me see if I had anything else to say before we discuss Weil spinner. Okay, I wanted to discuss one more thing. Just a small thing, but let's do that. The Lagrangian that we have written down, Dirac Lagrangian, this has a symmetry under psi going to exponential I alpha psi. Okay, just like our Klein-Gordon Lagrangian, complex Klein-Gordon Lagrangian was also symmetric under this kind of a transformation of field phi. You remember, because we had phi star as well as phi. The same thing is happening here. We have psi bar as well as psi. So when you take psi dagger, this becomes minus, and that exponential I alpha gets cancelled out. So this particular transformation of the Dirac's field is actually a symmetry of this Lagrangian. So it means you can get the corresponding conserved current the way we got for the Klein-Gordon field, and the conserved current turns out to be psi bar gamma mu psi. Okay, you can check this, but yeah, this is what I wanted to say before I go to while spinner. Okay, so psi L is left-handed while spinner. And psi R is called right-handed while spinner. How do they transform under the Lorentz transformations? So under let's consider infinitesimal rotation and boost. Call the rotation parameter to be theta. Boost parameters to be eta. Then, okay, let's recall. It was minus I over 2 omega mu nu is mu nu. So psi would transform as, now written in terms of these two component spinors, exponential minus I over 2 1 minus I over 2 omega ij is ij minus I over 2 omega 0 I is 0 I. Okay. This is equal to, okay, now this 2 actually gets cancelled out from the fact that omega ij is antisymmetric under the exchange of I and j. Sij is also antisymmetric under the exchange of I and j. So omega 1 2 S1 2 is same as omega 2 1 S1 S2 1. Okay, so this 2 gets cancelled out, and this 2 also gets cancelled out using the same argument. Okay, now what was Sij? If you recall, which we did today itself, it was sigma k 0 0 sigma k. Okay, and S0I was half of minus sigma I 0 0 sigma I. So we can substitute these here, and what do we get? Yeah, so we get let me write it down for psi L. Okay, so note one more thing. Omega ij, when takes values, let's say 1 2, that is nothing but theta 3.
Ma'am, before you proceed, just can you explain this left-handed and right-handed? Like, I don't know this.
Okay, this handedness we are now saying, but we are actually not explaining what is this, what does this mean by saying left-handed and right-handed. But we will come back to this when we explain helicity and so on. But right now I am not telling you why I am calling this left-handed and why I am calling this right-handed.
Okay, okay. I thought like it was said in before classes.
No,
Anyway.
no, yeah. We are just introducing why it's spinner, but we will come back to this when we discuss velocity and so on. Yeah, good question. We haven't said that. I'm just now telling how this psi L and psi R would transform under infinitesimal rotation and boost. So psi L would transform as, so you can see these matrices. If you substitute these matrices there, you get um, the following. So Sij will be replaced by this sigma matrices, and we have said that the take rotation parameters to be theta. So it becomes theta dot sigma by 2 minus was there a minus here or a minus here? Is in the definition is 0I. There was a minus in the first element. So, right. So this will become plus I beta dot sigma over 2 psi L. Okay, and likewise psi R would transform as under infinitesimal rotation and boost we are talking minus I beta dot sigma over 2. Okay. Okay, now if we substitute this in the Dirac equation, so let's see, Dirac equation is acting on psi equal to 0. What was gamma mu? So you just to avoid scrolling back and forth, I'm just repeating, but we wrote this before. It was 0 sigma I minus sigma I 0, I guess. So we can write this, we wrote this neatly as, sorry, sigma mu, sigma bar mu 0. Okay, so if we substitute it in that Dirac equation, we get the following: minus m I sigma mu del mu I sigma bar mu del mu minus m. This, now we are replacing the spinner in terms of left and right handed spinners. So if you have so we get two equations from here: minus m psi L plus I sigma mu del mu psi R equal to 0, and I sigma bar mu del mu psi L. Okay, so these two Dirac equation is basically mixing the left-handed and right-handed spinners. If we consider massless particles, then you get decoupled equations for left-handed and right-handed spinner, what you get is, these are called Weil equations. Sigma bar mu del mu psi L equal to 0. Okay. Okay, so this is what we wanted to talk about Weil spinner. For discussion, you should look at Peskin for more discussion, but this is what is pretty much there. Okay, now before we stop, let's discuss the solution of Dirac equation a bit. So, okay, so yeah, before we discuss the solution of Dirac equation, let's make another observation that I gamma mu del mu minus m psi, this was the Dirac equation. If you act by this operator, minus I gamma nu del nu minus m, what do you get? You will obtain, the first term will become gamma, just for, doesn't matter, but first term is gamma nu del nu acting on psi, or let me put psi outside. Cross terms get cancelled out. So the cross terms will be, you see that, right? The cross terms get cancelled out. I will not write down. Plus m square acting on psi equal to 0. Now, this is symmetric under the exchange of mu and nu. So the trivial thing to do is del mu del nu, and also note that these are dummy indices. So suppose we are exchanging mu and nu indices and writing that term again. Since we have written that same term again, we divide it by 2. Now del nu is same as del mu. So this implies we have written down gamma nu plus gamma mu divided by 2 plus m square acting on psi equal to 0. Okay, now use the Clifford algebra to rewrite the numerator. So that's 2 times g mu nu. So you recognize this, right? This is nothing but the anti-commutator of gamma mu and gamma nu. That is 2 times g mu nu. This implies so what does it imply? Each of the 4 components, you recognize this equation. What is this equation? Can somebody tell me?
Klein-Gordon.
Exactly. So each of the 4 components of Dirac spinner satisfy the Klein-Gordon equation. Which means the natural choice would be to take a spinner and a plane wave. So plane waves are solution to the Klein-Gordon equation, but now psi is a spinner. You can't just have exponential minus I p dot x, where p this P here is P mu 4 vector, P0 comma P vector, and P0 is square root of P vector square plus M square. So P square is basically M square, where P square is P mu 4 vector inner product. Okay, so now if we substitute that solution, let me put a heading, solution to Dirac equation. Okay, so if we substitute that solution in the Dirac equation, it becomes a matrix equation. So it was I del mu, sorry, gamma mu del mu minus M this will act on this exponential to give you I P mu, I gamma mu minus I P mu. Okay, and this is plus. So right now we are dealing with positive frequency solutions. P0 is greater than 0 minus M or plus, no, it will remain minus, right? Because that is I square, you will get minus 1. Okay, so that's what you have, where, okay, where U P is a 4 component. We are writing here P vector because P0 is given in terms of P vector only. So this U is a function of P vector is good enough. Is a 4 component spinor, is any arbitrary 4 component spinor. Okay, now, okay, so what is this how does it look like, that matrix? So let's write that down. What was gamma mu? Identity, and then sigma mu. Sorry, what was it? Gamma 0 was, sorry, I wrote something terribly wrong. This is gamma mu. What did I write there? Sorry.
Gamma 0 is like identity 0, 0 minus identity.
Exactly, exactly. I wanted to write this gamma mu, I wanted to write this, we defined as 1 comma sigma I. So which means when you write gamma 0, you will pick up sigma 0, right? And sigma bar mu we defined as 1 comma minus sigma I. So let me be clear about that notation. So when you write gamma 0, you mean you are basically picking up the 0th component of this sigma mu. So that will make it 1. Of course these are all 2 by 2. 2 by 2 identity, and sigma bar mu is also 1 for when mu is 0. And gamma I means you are picking up the ith component, which is 0 sigma I minus sigma I 0. Is this clear? This is what we started with, the while basis of gamma matrices. Clear? Any confusion? Okay. So what is gamma mu p mu then? It will be 0 p dot sigma bar 0. Okay, where p dot sigma is p mu sigma mu. So gamma mu p mu minus m acting on that spinner implies this minus m is multiplied by 2 by 2 identity, so you get minus m p dot sigma bar minus m acting on Is this clear? Are there any confusion? So this is a 2 by 2. No, this is actually a 4 by 4. These are all 2 by 2. So there is a 2 by 2 identity here. Okay. So the first easiest thing is to look at the solution in a frame where the particle is at rest. So in the rest frame, and then we will do the general solution. So in the rest frame, how much time do we have? 58, 48. Okay. In the rest frame, P vector is P0, comma 0 vector, and you know that sigma mu is identity, comma sigma I. So that implies we get minus m, call P0 to be m. I mean P0 becomes n in the rest frame because P0 was square root of P vector square plus m square. So this is m. Okay, and we said P0 is greater than 0, so we are taking the positive solution as of now. Then this is also m and minus m. So natural thing is to write u as, so the solution would be, which will satisfy this equation is, so I'm writing in the convention of Peskin's book. So this is square root m. So this is a convention that they have used, but it will become justified later on. Okay, so this is the solution, because this, when you hit by this particular matrix, you will get 0. The first component will be xi minus xi plus xi, so that will become 0. And from here also you get the same equation. So this is the solution, and label it by S, where S equal to 1 and 2. And you can see that each of these components transform under rotation like that of a spinner of 2 dimension, because remember Sij was epsilon ijk sigma k 0 0 sigma k. If you look at rotation about third axis, which means you are performing rotation in the 1-2 plane, this is equal to half of sigma 3 0 0 sigma 3. So that is how a spinner in your non-relativistic quantum mechanics transforms as. And you know that the two component spinners, you have two choice, like it can be either spin up or it can be spin down 0 1. So that's why we are labeling these by this index S, where S takes values 1 and 2. Okay, so that is a general solution. The solution when the particle is at rest, or we can write psi of x as us p vector minus I p dot x. Okay, and we will write down the general solution in the next class, but we need one identity. Let me just prove that for that. So p dot sigma times p dot sigma bar turns out to be m square. Let's prove this identity, then we can stop here. Are there any questions at this point?
Will you prove the identity now?
Huh?
You'll prove the identity now?
Should I not?
No, no, not in that way. Like, then after proving, then I will ask my question.
Oh, okay. Yeah, I will prove this identity and then we can stop. Yeah,
No, no,
you have
no.
a question. Yeah, ask me now.
Okay, actually, I was wondering here all this Dirac equation, Klein-Gordon equation, these kind of equations are derived from this dispersion relation, right? Dispersion relation means E square is equals to m square c to the power of 4 plus p square
These
c
are.
square.
Oh, you are saying that p square equal to. Sorry. I mean.
E square.
Yeah. Yeah. I mean, this is 4 vector. P square equal to m square. So if you write this in terms of all the quantum mechanical operators, you get the Klein-Gordon equation.
Yeah, and here if we write in only linear form, we will get Dirac equation, right? But when both the two equations are derived from the same dispersion relation, then why Dirac is perfectly fitting for fermions, but not for the bosons, but Klein-Gordon is perfectly done for bosons, but not for fermions.
Yeah, we'll come back to spins and statistics. We'll discuss all this. But Dirac equation is applicable for non-zero spin. I mean, Klein-Gordon equation is applicable only for spin zero, which are scalars. But in order to have spin half, you need this. You need this spinners and all, and for that you need a equation which is first order in derivative, and also the spin statistics we will discuss later on.
No, I got that. But what I was trying to say is like when both the equations are derived from one common equation, then why it is working completely different both the equations?
So exactly how Dirac came up with this Dirac equation is not by from p square equal to, but if you so from the Heisenberg equation, if we want to so okay, p square plus m square acting on psi, so this would be the relativistic generalization of Heisenberg equation. But this equation has got many issues in the sense that here it appears as first derivative, while here it appears as second derivative. But then the point was to consider this p square plus m square as a perfect square, like alpha dot p plus beta m. So because you are saying how these two are derived, that's why I'm telling this.
No, I know that, like I said, like alpha contains all the Pauli matrices and
Exactly.
beta is.
So alpha and beta are nothing but the gamma matrices that we wrote. So here it becomes, yeah. So Klein-Gordon equation is the most general the fundamental equation. Even you can see that all the components of the Dirac spinner also satisfy the same Klein-Gordon equation. That's why we are writing the solution in that way. Like it has to be a plane wave. which is also
Okay.
the case for a Klein-Gordon field, but those are just a scalar. So you remember from non-relativistic quantum mechanics, when you write down spinor, it is always a two-component vector, like 2 by 1 matrix. But just a scalar can't give you spin. So those 2 by 1 matrices were spin half particles in a non-relativistic quantum mechanics. So you need a vector formulation, and for this to be true, actually for this to be true, you can't have alphas to be just numbers. You have to have alphas to be vectors. um, I think.
And it and
And
as so I think like as we consider alpha with in some
do you
kind
know
of
which are?
Pauli matrices form, and Pauli matrices work for one half particles, Stern-Gerlach experiment.
Mhm.
So that's why Dirac
So
equation is
Dirac
perfectly
equation,
applicable.
yeah, it's you need matrices, and that is what you are getting in Dirac equation, but not in Klein-Gordon.
And these matrices are specially written in Pauli matrices because to satisfy this spin half particles. Pauli
Yeah, as of
matrices
now,
come.
whatever we are considering while basis, yes, the you can see exactly that the 4 by 4 matrix that you have. If you look at only just the 2 by 2 block, you see this is exactly how our two component spinor transforms under rotation.
Okay. And what if I write the same energy shell relation in some kind of the matrices which is corresponding to spin plus one or some any arbitrary spin, then will I get the equations related to those kind of particles which have that kind of spin? Just like Dirac have written in form of Pauli matrices and got Dirac equation. So in that way,
Sorry, can you repeat the question?
what I was saying is like Dirac have written all the matrices in the form of Pauli matrices, and Pauli matrices are corresponds to spin one half particles. Now, what if I write this energy mass relationship in the in some kind of other matrices? Think of n spin, like for nth spin, and there will be some associated matrix for nth spin, right? So will I get the equation which is applicable for nth spin particle?
Uh, I can't come up with explanation answer to that question. I think if you want to get some other spin, like instead of spin half, like you want to get spin 1 or spin 0. So yeah, so spin 1 particles are the fields corresponding to your electromagnetic theory, like uh,
Photon.
Maxwell's theory, which we also discussed the Lagrangian corresponding to that. If you quantize the Lagrangian corresponding to that, if you quantize your Maxwell field, then you get spin 1 particles. But how do we modify the matrices that we have in Dirac equation to obtain other spins? I'm not able to come up with an answer to that question. Maybe I'll think about it and get back to you.
Okay.
So let's do this. Okay, it will be a quick exercise, or I can give you homework. Would you like to do it in your? Okay, let me do it. So okay, so what was P dot sigma? I think we already wrote that somewhere. Oh no, we haven't. Okay, so what is P dot sigma? Uh, P0 sigma 0 was 1. So plus, so you have a 2 by 2 identity here, multiplied P0, then Px sigma x plus Py sigma y plus Pz sigma z. Okay, substitute all the sigma matrices that you know. So it's P0 0 0 P0 plus 0 Px 0 plus 0 minus I Py 0 what do you get? Plus pz px minus ipy px plus ipy p0 minus pz. Is that fine? And for p dot sigma bar, you remember sigma bar had a minus sign, so this will all be minus. So that means you get p0 minus pz minus of px minus ipy minus of px plus ipy p0 plus pz. Now you just have to multiply the two. This I would like you to do, and you should get m square times that identity, like 2 by 2 identity 0 0 2 by 2 identity. Okay, this you do before coming to next session. Okay, good. So yeah, are there any further questions?
One more question, but and the other thing is, like, because I was getting this doubts on this fundamental idea. So here, for quantum field theory, we are always writing Lagrangian to be Lorentz invariant, right? In fact, like, we are making a
Lagrangian to be a scalar always.
and Lorentz invariant quantum
So
field theory
any
is.
scalar transforms trivially. The scalar becomes just that thing.
Oh yeah, yeah. And we are making all the potentials in such a way that it will be a scalar and then so-called Lorentz invariance. So, like, why it is so necessary to make some kind of theory a Lorentz invariant theory?
Because we want it to be consistent with special relativity. That's the only thing we want to do now, right? Unlike non-relativistic quantum mechanics, we want our theory to be quantum as well as relativistic. So we have to make sure that whatever theory we are writing, it should be Lorentz invariant. It should be invariant under Lorentz transformations.
Ma'am, but the idea is like, ma'am, if we take any potential could be anything, right?
Yeah, you are probably thinking of like square well potential in quantum mechanics that you do. What will happen to that potential now? Is that what your confusion?
Yeah, kind of like.
Like, okay, so this I was thinking of, like, one more people asked me some time ago. I don't know whether it was some.
That was me only. That was me only.
Oh, okay. Okay. Yeah. So there's that potential. It's a square well potential. So you have a location. Let's say from x equal to minus a to plus a, you have zero potential, and at any other place you have infinite. So that's the infinite square well potential. Now, whatever we are doing now, we don't have anything in terms of x alone. Like, we have fields and we are ensuring Lorentz invariance of our fields, but we don't have. So remember, x, which is the position coordinate, is now acting as a label, and your dynamical variables are now the fields. Either it's phi for your Klein-Gordon theory, or it is psi for your Dirac theory, or it is maybe a mu vector field for your Maxwell's theory. But we are ensuring Lorentz invariance of these fields. We no longer have in the Lagrangian anything called x square. So that, I mean, x under Lorentz transformation will become lambda mu x nu, and you will end up having something bizarre, or under length contraction or boost, your the square well that you had will have now a different length or something. So I think there lies the distinction. I mean, if you are thinking of a potential like that of a quantum mechanics that you usually do, I think the theory that we are constructing is pretty much different from that.
Okay. Yeah. Okay, yeah, I got that. So you're basically saying here potentials are the function of field itself. So field phi. So that's why but still, even with field phi, the potentials could be exist in any kind of format, right? And it need not necessarily be Lorentz invariants.
No, no,
This entire Lagrange.
we are always ensuring Lorentz invariance. We are writing down the Lagrangian in a way that it becomes a scalar. So we are imposing Lorentz invariance in order to construct the theory at the first place.
So is it like nature prohibits the potentials which are not Lorentz, doesn't making the Lagrangian Lorentz invariant? Kind of.
I guess so. I mean, the quantum field theory has to be invariant under Lorentz transformations.
Hmm.
Yeah, I guess so.
Okay.
Okay. Let's stop here. Let's meet next week. Thank you.
Thank you, ma'am.
Yeah.